Right, this video introduces the use of Maclaurin series. In class, I will show you what Maclaurin series is doing to approximate a function, but the series has been developed to allow various applications, often in engineering. Perhaps we want to differentiate a function and we haven't got a method to do it, or we need to come up with some sensible approximations for a function, and it would make our maths easier and our answers suitably accurate if instead of using the actual function, we come up with a power series, so increasing powers of x that matches the function fairly accurately. Now, depending on the function involved and how many terms are taken, depends on how accurate the approximation is. Some are very accurate indeed and can be considered to be full expansions, and there are others where the value is very limited. Anyway, the method that we've got for approximating these functions is to consider the derivatives and to consider the derivatives at x equals 0. And if we can get those to match, we can then build up a series which is in this form. This is given to you in the formula book. And what we're going to do in the next two questions is we are going to show it in use. So let's have a look at question 1. We're given the function log of x plus 1, and we're asked to derive the Maclaurin series up to the x to the 5 term. So let's some space. So f of x is the log of 1 plus x. Now, as we go along, we're going to do the derivatives, and we're also going to work out the value of those derivatives when x is 0. So we'll do this alongside. So we've got f of 0, which in this case is the log of 1, which is 0. So first derivative is 1 over 1 plus x. Its value is 1 over 1 when x is 0, so it has a value of 1. Second derivative. I need to have this written as a bracket to the power of -1 so that I can use my chain rule. So it is going to be minus 1 plus x to the -2. Subbing 0 in. Again, the bracket will give us a value of 1, so the value of the second derivative with f naught in is -1. Let's consider the third derivative. So I'm using the chain rule again. I sub in 0 and I get a value of 2. Fourth derivative. Repeated chain rule. -6 plus x minus 4. Value with 0 subbed in, minus 6. And lastly, the fifth derivative, 24, 1 plus x, minus 5. So, I now have the values that are required to apply Maclaurin series. So, I'm going to be subbing in to this function here. So we have the log of 1 plus x, our original function, and it's going to be approximately equal to f of 0, which is 0, plus first derivative times by x, and the second derivative is going to be minus 1 over 2 factorial x squared. And the pattern continues. So it will be the third derivative, which is 2 over 3 factorial x cubed. Fourth derivative, minus 6 over 4 factorial x to the 4. And we're asked to go to the fifth, so that's 24 over 5 factorial x to the 5. Show the Maclaurin series formula with the various values subbed in clearly, and then simplify. So that gives me x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus x to the 5 over 5. So that's expansion. Now, it's not specifically asked for in this case, but sometimes you are asked to give what we call the general term. And I would work this out once I've done the expansion and simplified. So I can look at any of the terms and I can see that I need to have an x term to the power of r, where r is where I am in the series. So this is the fifth term, fourth term, third, second, first. If I go back up here, r will be 0 in this case. So in actual fact, we always do start with r equals 0, even if the simplification doesn't include it. So that's my x part. I then need to generate the rest of the terms. So on the bottom of the fraction, if I look at the row above, you can see that I have r factorial. I then, on the top, I've got a series of 1, minus 1, 2, minus 6, 24. Now, again, that in this particular case is a factorial, but it's r minus 1 factorial, which then allows it to simplify to just 2, 3, 4, and 5. That's where these simplified numbers come from. So now the only part that I haven't dealt with is the fact that I've got alternating positive and negative signs. So to generate that, I need a minus 1. I want the minus to be when I have an even power, So I need the power to be r minus 1. Check that works for a couple of terms. And there we have the general term for this particular series. Now, we need to continue to answer the question. It's asking us to come up with some approximations for particular values, but only using the first 3 terms of the series. So let's work through those. Part B then. So we've got the log of 1.05. I sub in to first 3 terms. That's going to be 1.05 minus 1.05 squared over 2 plus 1.05 squared over 3. That gives me an answer of 0.048792. If I compare that to the actual answer off my calculator, I would get 0.048790. So the approximation is correct to 5 decimal places. Now let's think about the log of 1.25. If I sub into the Mclarens expansion, I get an answer of 0.2240. If I compare that to the actual log of 1.25, that gives me an answer of 0.22314. So this one is correct to 2 decimal places. And then last but not least, to number 3, I've been asked to come up with the log of 1.8. The approximate value for that, having subbed into the Maclaurin series, is 0.651. The actual value for this one is 0.5878. So we could say, with appropriate rounding, that we're correct to 1 decimal place. Why have we bothered to do that? So that you can see that the further we are from 1, the less accurate the approximation is. And what we have is Maclaurin series, depending on the function, is only accurate for certain values of x. In the case of log of 1 plus x, the Maclaren's expansion is valid for minus 1 less than x less than or equal to 1, and that's its validity range. So in a similar way to when you were doing Maclaurin expansion, binomial expansions, certain series were valid for a particular range. That applies with approximations using the Maclaurin series. So that's the first example. Now the second example I've already done, so we'll have a look at my solutions. We'll follow the method and just understand what's going on with this one. So let's move across to question 2. We're being asked to find the first 4 non-zero terms of Mclarens for sine of x. So you would think to begin with that you will need to differentiate 4 times, but you're actually going to need to do it more often. And this is because some of the differentials, when we sub in the 0, give us 0, and therefore we do not get non-zero terms. So in terms of working, start off with my function sub in 0. That will not give me a non-zero term. Differentiate, sub in 0 and get 1. Differentiate again, obtain a value of 0. And differentiate again and obtain a value of -1. So you can see from here that when we sub into the Maclaren's expansion, we will get 2 non-zero terms. I need to keep going, which I do. And I now have 4 non-zero values, which means I will get the first 4 non-zero terms when I substitute into the Maclaren's expansion now. So I would refer to my formula book. I will show my substituting into the Maclaren's expansion clearly, and then I simplify and I come up with an approximation for sine of x as follows. So you can see there that we have 4 terms. I'm now going to be asked for part B to use the first 2 terms of the series to find approximation for the sine of 10 degrees. So this is included to remind you that we need to use radians because Maclaren's works when we have our trig functions in radians. So converting from degrees to radians, and then subbing in pi over 18 for x gives us an approximate value of 0.74. And that's Maclaurin series. In this case, I wasn't asked to give the general term, but I could work it through and derive a general term. So that's Maclaurin series when the question says, please use Maclaurin series as it has done here. Notice I've underlined the word Mclarens. The next video will explain about series expansions where it's based on Maclarens, but we have expansions already done for us.